Good morning, everybody. It's very dark and smoky up here on the stage, so we can't actually see everybody. It's a little bit mysterious. So thank you very much for getting up this morning and coming to listen to our talk about mobile point-of-sales terminals. So like everyone in the audience, we interact with payment technologies every day, but we're specifically interested in certain types of payment technologies. So today we're going to be talking to you about the vulnerabilities in mobile point-of-sales terminals. So mobile point-of-sales terminals has seen a huge growth over the last few years. We've moved from a single vendor dominating the marketplace, which is Square. They were the first vendors in this marketplace, and now there's several different vendors. So we've also moved from a very simplistic device to now incredibly sophisticated devices. You can get hold of a card reader for less than $50, and typically the sign-up process takes less than 5 minutes. So for these reasons, these devices have become incredibly popular, and you can find them predominantly in places like North America, and in Europe you can find them pretty much everywhere. So you can see examples of a taxi and a cafe, and that's also a gym that I've been to that has a mobile point-of-sales terminal. So for these reasons, they're also very popular with criminals, both for the testing of cards and for the movement of fraudulent money. But we weren't the first to investigate mobile point-of-sales terminals. In 2014, researchers from MWR Labs presented their findings at BlackHat on the Mura shuttle reader. So at the time, this reader was being white-labeled and used by a number of different vendors, and this kind of practice is still commonplace today. In their presentation, they noted a number of different vulnerabilities associated with the Mura shuttle reader, of which they shared very many common issues with traditional point-of-sales terminals. Then in 2015, 3 undergraduate students from the University of Boston presented their findings on the Square Magstripe reader. So we felt that both of these projects were really interesting and significant contributions to this area, but we didn't feel that they dealt with the more contemporary issues associated with these devices. Many of these devices are much more sophisticated than 3 years ago, and there's a lot more options in the marketplace. So we have many more vendors and many different types of card readers that we can now get. Okay. At the beginning of this project, we started with just 2 card readers and 2 vendors. But this quickly grew into a large project encompassing 7 card readers, 4 different vendors, and over 2 continents. So we set out to look and assess the most popular devices initially in Europe and North America, but this has now grown to encompass a few other areas as well. So we chose to assess PayPal, Square, iZettle, and SumUp. Now, some of these providers operate in different locations, and where possible, we chose to obtain accounts and readers in both geographic locations. That's because there's some significant differences between the processes and applications depending on the region that you're operating in. At the beginning of this project, we had a fairly good idea of the kind of attack vectors that these devices were vulnerable to, but we wanted to understand how probable these attacks were in practice. Still, we kept coming back to this very simple question, which is how much security can be embedded in a device that's effectively free? We chose to assess 5 different areas of the payment ecosystem. So the first is the communication between the phone and the payment server. Then we have communication between the device and the phone. Then we have the mobile application and associated mobile ecosystem. Then we have the hardware and the physical security mechanisms within the hardware itself. And then we have an area that we're calling secondary factors. So this is different mechanisms that occur during the process, such as the anti-fraud mechanisms or the checks that are carried out during the enrollment process. And they affect the overall security and risk of the ecosystem. But before we progress any further, I just want to give everyone a bit of background as to how payments traditionally work and how mobile point-of-sales terminals fit into this process. So normally, when you go to pay for something in a shop, say services or goods, you'll either hand your card over to the merchant or you'll interact with the terminal yourself directly. So once your card information has been read, this will be sent to the acquiring bank or that merchant. But at this point, they don't actually know who your issuing bank is. So they'll ask the card brands, such as Visa and MasterCard, to determine this information. This will be sent to your issuing bank, and they'll check that you have the necessary funds to complete the transaction and that they're happy for you to go ahead and make the transaction. So once they have decided that they're happy for you to do that, they'll send the response back along the chain, and you'll be able to complete the payment. If we take a look at what this looks like for mobile point of sales terminals, you can see that the key difference is that the merchant no longer has a direct relationship with the acquiring bank. Instead, the mobile point of sales terminal provider acts as an aggregator. So this means that they will or won't assess risk at the same level as a traditional acquiring bank. And sometimes they choose to mitigate some of that risk in other ways, for example, contractually. But the key point is that here what we have is two merchants in this model. So the mobile point of sales terminal provider are themselves a merchant as well. Next, when you go to make a payment, there are lists which describe the type of operations that you can actually make with your card and with the terminal. Broadly speaking, these go in order of most secure to least secure. So we can understand, generally speaking, that certain types of payments are more secure than others. For example, chip and PIN is considered high in its level of security because there's a high level of assurance that the cardholder was present during the transaction, and there's signing of the transaction, so there's a cryptogram associated with the transaction itself. If we compare that to something like magstripe, this is considered low in its level of security, and that's because I think most of us know that the data on the magnetic stripe of the card can be cloned, and the thing that provides the assurance that the cardholder was present during the transaction, the signature, can be forged relatively easily, and there's no cryptogram, so this is not a modern protocol. Next, we need to understand that while adoption of EMV or chip has been incredibly successful in some areas of the world, it's actually been a bit slower in some parts. So, for example, if we look at North America, actually the rollout of chip has been incredibly slow. And this is in part due to the number of parties involved in the rollout process. So there's a large number of different banks, and it's just taken a bit longer for that reason. But the benefit of understanding this information is that we can look to other parts of the world. So we can look to South America and we can look at Europe, and we can see what kind of attack vectors have happened historically, and also use those as a good predictor of what might take place in North America. So if we look at this picture in a bit more detail, you can see in North America that EMV has actually been adopted quite widely in terms of credit cards, but less than 50% of any transactions are actually made using a chip. And that's actually even worse when we look at debit cards. Less than 25% of any transactions are actually made using a chip. And finally, it's really incredible to see only within a couple of years that in this marketplace with mobile point of sales terminals, there's been a huge growth. So by 2019, we can expect that almost 50% of all transactions made via a terminal will actually be made via a mobile point of sales terminal. So this schematic overview represents how each of the components in the system communicate with each other. So we have the mobile point of sales terminal, which communicates via Bluetooth or the audio jack to the phone, and this in turn communicates via Wi-Fi or over a network connection to the mobile point of sales terminal provider. So now that we have a broad understanding of how payments work and how mobile point of sales terminals fit into this process, we can begin to discuss the findings. So we're going to be talking about the sending of arbitrary commands. This allows us to socially engineer a cardholder to do things like downgrade the transaction method from something like chip and PIN to magstripe, and we can also use it to interact with the payment process. So for example, we can display a message such as payment declined or payment cancelled, and we can force the cardholder to carry out an additional transaction. Then we'll be talking about how, for some of the readers we looked at, we were able to modify the amount. So this means that we can display a much lower value on the terminal and force a cardholder to carry out a much higher value transaction without actually realizing this. We're going to talk about how we obtained remote code execution on the Mura M010 reader, and this is available through a number of the vendors we looked at, for example, Square and PayPal. And this allows you to have full access to the operating system. So once you have full access to the operating system, this means we can do things like intercept track 2 information before it's actually encrypted, and we can enable the plain text mode on the pin pad of the device, so we can start collecting pin codes as well. Then we'll talk about the physical security mechanisms in these devices, and then finally we'll talk about the secondary factors. So Bluetooth is the main form of communication between the device and the phone, so therefore it's important for us to have an understanding of how this protocol works. So Bluetooth can be roughly divided into the host and controller layers. So the Bluetooth profiles and GATT and AT, they deal with the actual transfer of information. Then we have L2CAP, and that deals with the segmentation of the packets. Then we have the host controller interface. Now, many of us actually have worked with the host controller interface. This is commonly used for debugging. So this is the lowest layer that we can directly interact without specialist equipment. Then we have the link manager protocol, and this deals with the pairing, negotiation, and encryption. And we have baseband, which is the final layer of framing before Bluetooth radio itself. So when we talk about Bluetooth, we're actually talking about 2 distinct protocols. The first is Bluetooth Classic, and then we have Bluetooth Low Energy. So how these communicate to devices or between the phone and the device is quite different. So with Bluetooth Classic, all of the terminals that we looked at, they use RF COM for communication. So what this means is that you can initiate a connection from the phone to the device, and you simulate a serial port. This means that we can send a large stream of data to the device. On the other hand, when we look at Bluetooth Low Energy, the structure of sending data is quite different. So it has a hierarchical structure under which services and characteristics are defined. And then we have values for each characteristic, and that also has some properties such as read, write, and notify. The main difference with Bluetooth Low Energy and Bluetooth Classic is that the data size is quite restricted. So for Bluetooth Low Energy, once you've taken away the headers, you have about 20 bytes that you can actually send information for. Now, in order to attack a Bluetooth device, we actually need to know what its address is. The address is made up of 3 main parts. So we have the non-significant address part, which isn't significant for any features or functions. Then we have the upper address part and the lower address part. So the lower address part, that's unique to every device, and this is present in every frame of communication. The non-significant address part and upper address part are what is known as the organizationally unique identifier, or OUI. So if you're an attacker and you know what the OUI is for a given device, so each vendor is assigned a range of OUIs. So if you know what the OUI is for a specific terminal, this means that you could go and sit in a public place and you could identify potentially vulnerable terminals. So there's many different Bluetooth attack vectors, but we're just going to be focusing on 2. So the first is eavesdropping, or man in the middle. And the idea is here that you're trying to intercept connection between the master and the slave in the network. And the second attack we'll be talking about is malicious device manipulation. So with this, you're just connecting directly to the device, and you're trying to get it to do some things. So it might be that some of these functions are intended by design, or it may be that you're trying to get it to do something that's quite outside its intended design. So with a man-in-the-middle attack, what you're trying to do is follow the connection between the master and slave, and collect enough information so you can decrypt the communication. Now, how you carry out this attack depends on the Bluetooth communication type. So if it's Bluetooth Classic, if it's a device that's reasonably sophisticated, chances are it's using something called an enhanced data rate. Now, the problem with this, from the attacker's perspective, or if you're a security researcher, is that it requires dedicated equipment to actually carry out a man-in-the-middle attack for this type of device. So typically, this equipment retails for about $20,000. So you can see the frontline BPA 600 there, which means that this kind of attack vector isn't very viable for most of us. For Bluetooth Classic, for Bluetooth Low Energy, on the other hand, it's much easier for us to find equipment that we can use. So we can use something like the Ubertooth one, or there's also the Texas Instruments CC2540 dev kit, which is also available, and that's around $50. So it's pretty cheap. But carrying out these kind of attacks are quite difficult if you've had any experience with them, and there's a lot of room for error. Also keep in mind when you're thinking about a man-in-the-middle attack, we're talking about payment terminals. So a lot of the pertinent information is going to be encrypted from the terminal all the way through to the payment server. So for us, when we were looking at these devices and trying to carry out these kind of attacks, it wasn't a viable attack vector. Just a quick note on enhanced data rates, because there isn't that much information available to find out if a device is using an enhanced data rate. So how do you confirm that your device is using an enhanced data rate, and therefore you probably can't carry out a man-in-the-middle attack? So you do two things. The first is you run a reconnaissance scan against the device using something like HCI tool, and you'll see that EDR is actually listed as a supported feature for the device. And the second thing is you can use a tool like Ubertooth to collect some of the packets, and you'll notice that you're only actually collecting the headers and there's no data payloads. So this brings us on to our first finding, which is the sending of arbitrary commands, which, as I mentioned, we can use this to our advantage by actually socially engineering the cardholder. So how do we carry out this kind of attack? Well, the first thing that we need to do is we need to connect to the device, and we need to understand how the device actually works. So what each of the functions are responsible for and how we communicate and initiate those functions. We also might need to understand how the pairing process works. For example, for some terminals, you might have to have some physical interaction to initiate the pairing process in order to connect. So we need to keep that in mind as well. So before you carry out this attack, you need to carry out some prerequisite work, which you'll need a mobile phone, and you'll need access to something like developers options to enable the HCI logging. This is going to give us a lot of information about the communication between the phone and the terminal. Then you'll need access to the mobile application and the terminal that you're intending to attack. So now we want to carry out a sample of transactions, and this is so that we can get an idea of how each of the functions work. So here you can see I've imported the HCI log into Wireshark, and for this specific device we can see the sending of the message insert or swipe card to the device. So here's another example. So what I've done is I've inserted my chip card incorrectly into the terminal, and it's produced a message that says, "Please remove card." So here we can see that there's actually two packets responsible for the sending of this information, and that's because this terminal is using Bluetooth Low Energy. We can also see the UUID value responsible for it and the value itself. So we need to know this information in order to communicate with the device. So we use this information along with the information that we can obtain in the mobile application, and it means that we can actually work out what the message consists of. So it consists of 5 main parts. So we have the leading part, and this contains a counter, a command ID, and the intended payload size. Then we have the message, which is "please remove card," and that's in ASCII text. Then we have a trailing value, which is always consistent, a checksum, which is in X modem, and then the end value is also always consistent. So what can you do with this kind of information? So as I mentioned, you can force a cardholder to actually carry out a more vulnerable payment method, such as magstripe, and we can also interrupt the payment process. So we can display a message that says payment cancelled, even though the payment's going to go through. So let's take a look at this in action. So here I've got a terminal that I'm going to connect to, and first of all I'm going to ask the cardholder to insert their card. And then I'm going to ask them to swipe the card instead. Okay, so here's another example. You can see that this looks a bit different. That's just because this terminal is using Bluetooth Classic, so we can see all the data has been sent in one long packet. So here we can see the sending of the message insert or swipe card to the display of this device. And again, what we can do if we deconstruct the message, it's quite similar to the previous example. So we have a leading part. This contains a command ID, the payload size, and a counter. Then we have the message, which is in ASCII, which is insert or swipe card. And then we have a checksum, which is just a simple XOR calculation. So what we're going to do with this example is we're going to interrupt the payment process. So here the cardholder is carrying out a contactless payment for £1. But what we're going to do is we're going to connect to the terminal and we're going to say, actually, this payment isn't going through. So you'll see in a moment that it's going to say payment cancelled. But in fact, this payment has been authorized, which we'll see on the phone. There's going to be a text message that the cardholder receives for the value of the transaction. So unless you have this kind of alerting enabled through your bank account, you wouldn't actually know that the payment has been authorized. Yeah, it's not. Okay. So what else you can do with this kind of information is we realize that we can actually use this to fuzz for different kind of vulnerabilities. So you do this by connecting to a potentially vulnerable terminal, and then you send an increasing number of characteristics to that value that we identified, which causes the terminal to do things like restart or crash. So what we decided to do is we decided to implement this using a very simple program on the ESP32, which is a really cheap device that you can get for less than $15, and it's very compact and low power, and it supports both Bluetooth Classic and Bluetooth Low Energy. So here you can see in this example, we're going to see on the left-hand side is the output from the ESP32, and we're sending, you can see the little bunny on the terminal, we're sending an increasing number of characteristics. We're going to hit 32,776 characters, and then it disconnects. So you can use this as a method for identifying other vulnerabilities in the terminal. So this brings us on to our next finding, which is the modification of the amount, which Tim's going to talk to us about.
Yeah, thanks. Now let's try to intercept and modify payment process. So there are actually many ways to intercept payment comments as well as other comments to the reader. First of all, most of them are going from a server side, which means that we can intercept them via HTTPS main in the middle. And for this purpose, you need to bypass SSL pinning somehow, but if it is your device, and especially if it's rooted, it's not a big deal. Next method was already mentioned, is just to enable HI login on the device and collect data and read it via Wireshark. Also, what else you can do? You can rebuild an application and enable debugging messages and then get access to them via Android debugging bridge, as well as reverse engineering of application is quite useful to understand the structure of comments, get example of example and descriptions of every other comments and so on. And finally, if you don't have any other options, you still can use some external device such as Bruteforce to get access to the traffic. So here are two examples of intercepted payment comments from two different readers. And for each example, we used two different channels of interception just to correlate the information. And in the first case, we rebuilt an application and we also enabled HI login. And as you can see, we made a payment for $750 and amount was actually sent in hex, so 02EE. And in the second case, we also rebuilt an application and enabled HTTPS main in the middle. And in that case, amount for payment was sent in plain text, so 0100. And as you can imagine, in both cases, just to change any amount to this amount to any amount you want, you just need to change those bytes and replace a checksum. So what actually will happen if a fraudulent merchant tamper the amount between reader and the phone? It will be possible for him to force customer to make a higher value transaction by showing lower value amount on the reader and on the phone, but actually sending higher value to a server side. So that's actually what we did. So we sent £1.23 to a server, but customer actually sees and confirms only £1 transaction. And as you can imagine, we don't even need to forge a signature because customer will leave his own genuine one. So this type of fraudulent payments will work at least for MaxStripe. Why? Well, simply because during the MaxStripe transactions, reader will not send anything except track2 data, encrypted track2 data. When, for example, for chip and pin transactions, an actual amount that was signed and currency that was signed will be sent in a cryptogram. In these terms, contactless transactions are very interesting because there are certain modes, legacy modes, which also allow to send data and will not send amount and currency. And these types of transactions also can be affected. And finally, the limits for every kind of transaction for payment providers are absolutely insane, for like up to $50,000 or pounds depending on the region, which means that service providers rely only on issuing and acquiring bank in terms of blocking of fraudulent transactions. So let's imagine ourselves. We can open a merchant account in less than 5 minutes. Then we can force customer to use less secure form of payment, for example, MaxStripe instead of chip and pin. Then we're going to show absolutely random amount on a screen of a reader and on a phone, like $1, for example. But actually, it will be possible for us to carry out transaction for up to $50,000 a time. And the last problem is that for some readers, it's even possible to make this transaction with some significant delay. For example, 10 minutes after customer has already swiped card and has already left the building, which is quite useful for fraudulent merchants. As we mentioned, in Latin America, there are a lot of different mobile point-of-sale vendors like SumUp or iZettle, but we just decided to find some really local vendor, and that's how we found Clip, which operates in Mexico, has 2 different readers, and we actually wasn't able to obtain an actual account because we had to find a local phone and banking account. But what we found a debugging application from the vendor, and by design, it's quite interesting. By design, it should work with chip and pin, MaxStripe, and contactless transactions, but surprisingly, it actually doesn't work with contactless transactions at all, because it says that it should work with Samsung Pay only, and when you actually tap your Samsung Pay, it works as a MaxStripe emulation. So actually, NFC reader doesn't work in these readers at all. So, as you can see, here is a Dispret QPOS Mini reader manufactured by Chinese company Dispret, and they have a demo application which you can download and use for debugging information. It's very useful to get format of messages. That's how with this application, we realized that encryption works with algorithm which calls DuckPT, which is kind of basic standard for sending of payment information in an encrypted way. And after intercepting of sending of payment commands, we also made kind of reverse engineering of structure, and you can see leading part, which also will contain size, counter, type of command. Then we have payment information itself, which will contain amount, currency, timestamp, some additional information such as type of transactions and so on. And some trading part, which also will contain some checksum, which we didn't reverse yet. But what we actually found is that for creating a payment command, you don't need to connect to the server at all, which means you can create your own payment commands if you will be a fraudulent merchant and send it to a device pretty much the same way as we shown before. And because there is no signs of what actual payment was, the amount for payment that was made for MaxStripe transactions, you can see that basically this reader will affect by our findings as well. So what actually we'll do with all of this? First of all, we obviously recommend that if you as a service provider won't be able to change specification of communication between reader and the phone, if you don't have a firmware for a reader, you still can mitigate these risks. It's quite essential to control your mobile ecosystem and should not allow to use rooted devices, because rooted devices is a just direct way to reverse engineer the structure of commons and tamper any data fraudulent merchant will decide to make. For customers, recommendations is much easier, just do not use Maxstripe. What also we found is that sometimes it's much easier for hackers to get a full access to a mobile point of sale reader than to traditional terminals. So all you need for this is just to get a good reverser, which surprisingly works in our company, and get an encrypted firmware. So let's briefly describe how firmware updating process work in the readers. Depending on readers, depending on companies, there are many ways to deliver updates on a device. Some companies send updates as a set of encrypted commands, which are then translated via Bluetooth. Some of them send in updates as links to encrypted firmware, as you can see on the slide. And in this case, you can try to enumerate and obtain some older versions of a firmware or some debugging versions of a firmware. As you can see, we did found like previous version. But sometimes you don't even need this. You don't need even to open an account, having a reader or anything like that. So all you need is just to use Google and find some repositories which will lead you to unencrypted firmware. So why it's so interesting in what unencrypted firmware will contain? Well, first of all, it is a whole set of all configuration files which say what type of messages should be displayed, what messages should be displayed, what type of operations should be supported. That means that if you will change these configuration files, you can disable chip and pin, for example. And finally, it is a whole set of binary files which are responsible for handling information, and in them you can find remote vulnerabilities, as we did. So in the end, we found the remote code execution via Bluetooth, which gave us full root access on a reader, which is quite good because initially we didn't expect anything like that. So why it is so important to get a fully compromised mobile point of sale terminal? One of my favorite cases happened here in Latin America when in 2014 hackers made fraudulent payments for thousands of dollars using stolen track-to data. The problem was that they used mobile point of sale terminal, infected probably the same way as we described before, and they carried out the fraudulent transactions with stolen track-to data. The problem was that they were trying to convince the issuing bank that transactions were chip and pin. And the most curious thing is that original cards didn't even have chip on board. So that's how basically acquiring bank in the end found out that that was just type of unusual fraud. Next, the first thing that pops up in our head is just to try to collect track-to data before it will be encrypted and try to collect unencrypted PIN codes. So as we found out, the MPOS work pretty much the same way as traditional terminals or traditional ATMs. So PIN pad has two modes. It has encrypted mode for entering PIN code and has plain text mode for entering some additional information. Yeah, and if you have access to a binary file which is responsible for switching between these two modes, you can manipulate this information and force customer to enter PIN code and encrypt it. And finally, this small piece of hardware is very useful to understand how payments work in general, how payment researchers were working on their projects before and create your own security research, basically as we did. Last problem is that we need to keep, as it say, persistence on a device, because device potentially have two problems. First is that it controls its own integrity after each rebooting, and with digital signatures we need to substitute our our signatures for changed files. And we were able to do this by just changing these signatures because it's allowed to use self-signed certificates. And finally, mobile application also has to check out-of-date firmware and should not allow to use out-of-date firmware. And all you had to bypass this check is just to drop a packet with request or response for a server, and mobile application took like a couple seconds, and after timeout came back to you by saying, okay, I don't care what firmware version is, I'm ready to work. So in this case, imagine that you as a fraudulent customer can get access to a device for a couple seconds, switch on the pairing mode, connect your own malicious device, and send an exploit and get a remote code execution on the device. Then you can bypass updating process and start to collect track-to data and encrypted pin codes and send it to your own server. So for these problems, we recommend obviously not allow your customers as a merchant to use out-of-date firmware, and especially downgrade firmware, because this is completely unnecessary. And we obviously decided as soon as we got a remote code execution to put more cats on the internet, and that was the moment when smoke should appear, but I'm sorry. Yeah, so, and finally, speaking about hardware, yeah, surprisingly, with these small and cheap $50 devices, hardware protection in most of them are quite good. So most of them has anti-tampering mechanisms, such as anti-tampering foil circuit, protection against drilling, opening, sometimes even pressure sensors. And the last problem is that even if you will get access to internals without alerting anti-tampering mechanisms, all you will find only is a set of proprietary protocols, sometimes no GTAG, which means that without developers' documentation, without developer certificates, you hardly will get anything.
So this brings us on to our secondary factors. So as we mentioned at the beginning, there are quite significant differences depending on the vendors. So we found that actually the level of maturity in the marketplace isn't that sophisticated when you compare it to traditional banks. So if you look at the kind of checks that are carried out during the enrollment process versus the kind of sophistication that you have to go through with a normal bank, it's very, very different. Also, when it comes to things like transaction monitoring, we found that most of the vendors were very simplistic as to how they look at the transactions. So they typically only look at a small portion, a small sample of transactions for the overall volume of transactions that you're making, and they only look at very simplistic measurements of fraud. We did find that one specific vendor was quite sophisticated in this area, so not surprisingly, Square are quite sophisticated, but that's because they've been around for a long time. So they started out, they were the first vendors in this area, and in addition to that, they also had, for example, they had a lot of publicity around some of the findings. For example, the students who presented their findings on the Magstripe reader. And because of that, they decided to open a bug bounty program. And we think that because of these reasons, they're quite sophisticated in terms of how they approach security and transaction monitoring. So they actually correlate on a vast number of different data points, which means that it's quite hard to be a fraudulent merchant or to do anything really suspicious with an account. Even if you then move to a different device or you create a new account, they're very, very good at actually identifying suspicious accounts. And as I mentioned, there are some differences depending on the geographic location. So generally speaking, we found that devices and readers in Europe were far more restrictive than those elsewhere. So for example, in the US, you can carry out offline processing, offline transactions, and MSD transactions, and we can't carry out these kind of transactions in Europe. We also noticed that for most of the vendors, they weren't protecting the mobile ecosystem. So this is what allowed us to get access to things like the HCI logging, which provided us with a whole bunch of information that we can then correlate with the mobile application. So when we spoke to many of the vendors, what they said is that we consider the phone to be already compromised. Of course, the problem with this approach is that if you consider the phone to be already compromised and you don't want to implement any security mechanisms is that anyone can reverse the structure of your device, which isn't very good. So this table represents a broad overview of all the different devices, vendors, manufacturers that we looked at, and all the different areas of assessment that we carried out. So as is probably quite obvious to everyone, the marketplace places an emphasis on usability. And this is because they're trying to get as many customers as they possibly can. The only issue with this is that most of the vendors, so almost all of them, don't actually have very high security standards, which they should in fact have. Because if you lower the entry barriers to your payment ecosystem, you should in fact have very high security mechanisms to counteract the fact that you're letting everybody in, which isn't the case. So during this project, when we looked at our findings, we found that almost all of the vendors that we looked at were actually affected by the findings. And more than half of the readers that we looked at were affected by the vulnerabilities that we identified. So they were quite far-reaching findings. So what does this mean, broadly speaking, for looking at risk? So it means that if you're a merchant and you actually process card transactions, you shouldn't use magstripe. And it's not just because of the vulnerabilities we identified within mobile point-of-sales terminals, but it's because this protocol is actually deprecated. So as I mentioned at the start, it's relatively easy to clone the magstripe from the back of the card. You can forge a signature relatively easily, and there's no signing of the transaction. And if you look at how liability sits for this kind of model, we find that actually merchants inherit all of the liability for a transaction. So it means if you're a merchant and you're processing magstripe transactions, it means that if anything bad happens and the mobile point-of-sales terminal provider or the bank identifies an issue, it means that you'll get something called a chargeback. So ultimately, all liability associated with magstripe sits with the merchant, which isn't very good. So as a result, we recommend that everyone just uses chip, as this is a good way to protect yourself. But more broadly speaking, when we think about the kind of issues that we're seeing with this marketplace, it actually applies to many different areas of business. So we've seen a huge growth in embedded systems being used for both consumer products and products that have been integrated into businesses. But I think we all need to keep in mind that most of these vendors have only been around for a few years. So what this means is that the product is probably not going to be as developed as something that's specifically developed for a corporate organization. So we found that many of the products that we looked at, the security mechanisms weren't very sophisticated, which is what you would expect, but I don't think many of us consider that when we're integrating these products into our businesses. So this brings us on to our conclusions. So for manufacturers, we recommend that you implement control mechanisms over firmware, so that's encrypting and signing firmware. This helps to prevent against the modification and interception of firmware via sniffing. We also recommend that you use a Bluetooth method that visually confirms the pairing of the intended device and the phone. And that's because many of the issues that we identified involve some level of physical proximity to communicate with the device. So it's a good idea to implement mechanisms which confirm that you want to pair the intended device. We did see good evidence of security mechanisms in the physical security, but we didn't see good evidence of security being looked at overall in the entire ecosystem. For vendors, we recommend that you support deprecated protocols like magstripe, and you can do this by implementing some sort of signing on the server side, for example, or you can offer the ability not to actually take magstripe transactions at all. We also recommend that you use very good, strong preventative monitoring practices. So this looks like correlating on vast different points, which is a very effective way of identifying fraudulent merchants. So instead of just specifically looking at the transactions and whether they look suspicious, also looking at what kind of account activity looks like overall, where the location of the device is it a rooted device, have they got developers options enabled, those kind of mechanisms. We also recommend that, again, you protect the use of firmware. So that means that you should control the versions of firmware. So as we found that there was a version of the PayPal firmware, an outgraded vulnerable version available online, it's a pretty bad idea to do that kind of thing. So it's really important to implement good practices around that. And of course, you should place more emphasis on enrollment checks. That's because this is really the gateway to the mobile point of sales terminal ecosystem. So it's really important to carry out very good checks during the enrollment process, such as carrying out fraud checks and running a credit check as well. For merchants, it's fairly simple, so we recommend that you don't actually process magstripe transactions, and that you control physical access to devices so that you can prevent things like modification. And as we mentioned, many of the attacks involve some level of physical proximity initially to carry out the attack. And if you are a large merchant, so some merchants do have a large number of these terminals, it's a good idea to actually carry out an assessment of the environment. So that concludes the presentation of our findings, and I just want to thank you very much for listening to us this morning, and also just mention a couple of our colleagues who helped us. So Artem did a huge amount of work reversing the Mura M010 firmware, and then also mention to Alexei and Mark, who helped us look at the physical security mechanisms within the hardware itself. So if you have any questions, let us know, and thank you very much.